Okay, so you've seen a few examples now of Kirchhoff's loop rule, which is a statement of the law of conservation of energy as it applies to electric circuits. Here we have Kirchhoff's junction rule. The junction rule is a statement of another conservation law, law of conservation of charge. Actually, charge per unit time, which is really current. In other words, Kirchhoff's loop rule says the total current flowing into a junction is equal to the total current flowing out of that junction. So let's say there's some current that flows through this resistor number 1. Well, that current, here represented by, here I'll use lowercase I instead of capital I. So we'll say that current through resistor number 1 is I1. Now, that current reaches a junction. It splits up into two paths. Some of that current is going to flow through the resistor on the left, and of course some of that current is going to flow through the resistor on the right. So we can label these as different values of I. How about I2 and I3? Well, the analogy I like to use is the analogy of cars driving down a highway. We can think of those like, instead of the flow of charge, we have the flow of vehicles. And here we have a junction. Cars can continue straight down this path. So we have some number of cars that reach our junction. So we can say that represents the amount of cars on segment 1 of the highway, and then that highway splits off into segment 2 and segment 3. So imagine standing here and just keeping track of how many cars are entering this junction in any given amount of time, and then how many total cars go past the junction. Well, if there's a different amount of cars entering the junction in 1 minute than there are leaving the junction in 1 minute, that would be really confounding. Where the heck are the missing cars going, right? If the amount of current that flows into this junction doesn't equal the total amount of current flowing out of the junction, that's very confounding. Where else could the current be going? So, Kirchhoff's loop rule. The total amount of current in equals the total amount of current out. If I were to apply it to this specific example, we would say I1 is equal to I2 plus I3. It's really that simple. So we can see Kirchhoff's junction rule applied to this example circuit. Number 1, identify where the junctions are located. So there's a junction here, we might call that X. Another junction here, we can call it Y. And so we can label the currents. There's some current that flows through the battery and through the 12 ohm resistor. So we'll call that current I1. That current reaches the junction at point X, and some of the current then flows through the 8 ohm resistor. We'll call that I2. So beyond that junction, the current represented in orange as current labeled as I1 splits off. Some of it takes the path shown in green. Some of it takes this path shown in blue. This current I2 is flowing out of junction X. This current I3 is also flowing out of junction X. The current I1 is flowing into junction X. So again, I1 is equal to I2 plus I3. Now this happens to be a reducible circuit. Let's see, the 8 and the 24 are in parallel with one another. So we say 1/8 plus 1/24. Oops, what did I say? 12 plus 1/24. That's the same thing as 3/24 plus 1/24, or in other words, 4/24. Of course, that's not what the equivalent resistance is. That's the inverse of the equivalent resistance. So the equivalent resistance is 24/4, which is equal to 6. So if I wanted, I could think of this as a 12 ohm resistor followed in series by 6 ohms of resistance. In other words, this current I1 is flowing into this junction at point X, and then it splits off into I2 and I3, but I'm combining those two resistors as one. So this is I2 plus I3 combined. Okay, the equivalent resistance of a 12 ohm resistor and a 6 ohm resistor in series is 18 ohms. And when 18 ohms is powered by a 36 volt battery, then the total current is equal to 36 volts divided by 18 ohms, which is 2 amps. By the way, the total current is this current I labeled as I1. That's, in other words, the total current through the battery, which also happens to be the current through the 12 ohm resistor. If Ohm's law is right, and it is, V equals IR, so 2 amps times 12 ohms gives us 24 volts. So if the electric potential here is 0, here it's 36, there's a loss of 24 volts across the 12 ohm resistor, so 36 minus 24 gives us 12, and the potential at point Y is 0. So the potential difference across this 8 ohms of resistance is 12 volts. I is equal to V over R. So 12 volts divided by 8 ohms gives 1.5 amps. So of the 2 amps that flows through the 12 ohms of resistance and reaches this junction at X, 1.5 of those 2 amps goes through the 8 ohm resistor. So to figure out how much current goes through the 24 ohms of resistance, we have now 2 ways that we can solve for it. One, we could just use Ohm's law, say the electric potential drops from 12 volts down to 0 volts as it encounters a path of 24 ohms. I equals V over R, so 12 volts over 24 ohms gives 0.5 amps. Oh, and then notice, looks like Kirchhoff's junction rule was correct. The currents coming out of junction X are 1.5 amps combined with 0.5 amps to give us 2 amps, which was the current flowing in. So that would have been the other way to solve for the amount of current flowing through the 24 ohms. We didn't actually have to apply Ohm's law. We could just say 2 amps are flowing in, I1 equals I2 plus I3. So I3 must equal I1 minus I2, which is 2 amps minus 1.5 amps, which is 0.5 amps. Another thing we notice is the ratio of resistance here. In this example, it happens to work out to be a whole number ratio. If we say the resistance of the 8 ohms is just some value we call R, then the resistance here is 3R. So if we just guessed at it to start with and said the current that we labeled as I3, if we just call that X, then it's a pretty safe guess that the current flowing through the 8 ohms of resistance would be 3X. When it's 1/3 the amount of resistance, it's 3 times the amount of current. So by the junction rule, two amps is flowing into our junction X, and then there's a current we just call X here, and there's a current we call 3X here. So the one thing we know is, oh, and by the way, this is I2, this is I3, so I1 has to equal I2 plus I3, so 2 amps has to equal 3X plus X, or 2 amps has to equal 4X, so X is equal to 0.5 amps, which means then 3X would equal 1.5 amps, which is exactly what we got. 1.5 amps and 0.5 amps. Hey, how about that? So, Kirchhoff's rules. Loop rule. The net change in voltage, or the net change in electric potential, I should say, around a loop is equal to 0. That follows from the law of conservation of energy. Junction rule. The total amount of current in equals the total amount of current out. Oh, by the way, one last double check here. There is another junction at Y. Now what current is flowing into it? This current I2 flows into junction Y. So does the current I3, and then the current flowing out is I1. So in that case, we would say I2 plus I3 equals I1, but we know this is 1.5 amps plus 0.5 amps, and that adds up to give us 2 amps. And so if this is 2 amps, that 2 amps goes through the battery, and it's the same 2 amps through the 12 ohms of resistance, and there we go. Wow, it all checks out.